In the echo verification, we needed that control qubit to measure expected values. And here we're going to do a control-free version by preparing an initial state where our unitary acts as an identity. And that was a trick that was discussed earlier. And so for this circuit up here is describing the echo verification circuit. We run it forward, we measure the expected value. This extra circuitry is actually measuring for the all-to-all Hamiltonian that we have. Then we run it backwards and we post-select. So down here is sort of a review of all of these settings. This was run on the Sycamore device on a 25-qubit subgrid. Each of the GS gates here involve 3 CZs and 2 microwave gates. Each of the GS gates we calibrate to a precision that's has a standard error of 10 milliradians. If we see that the calibration goes above that, we stop the experiment and recalibrate. So this is about 162 qubit gates on the 10-qubit experiment. Okay, so how did this perform? On the right here, what I'm doing is I'm taking that Richardson Goddard Hamiltonian and I'm changing G for 10 qubits. For virtual distillation, this is for 10 sites. For virtual distillation, this is 20 qubits. And as I change G, I'm also going to look at the performance of pair double cluster doubles, which is a classical method and PCS theory. The nice part about this is that these yellow and green, those are our arithmetic data points, lie right on top of our line here, while there's a considerable energy error if you look at the post-selected BQE results in red or just the raw BQE results that we're getting from running the circuit forward. And so on the right here, this is just the energy error zoomed in. So that's quite nice. As we showed earlier, the echo verification and virtual distillation are quite similar. In this case, we're using 2 copies, and so they're actually error mitigating to a similar quality. And we'll say that that virtual distillation actually requires far fewer overall measurements. That's actually because we tried in echo verification to add some time dependence to the observables that we're measuring, and this actually lets us subtract any constant magnetic field that the qubits are feeling. And so it's just an extra error mitigation. I think Glasgow this morning was talking about how they have to corral many different types of error mitigation, and we did the same thing in this experiment. It involves dynamical decoupling for idling and deleting extra identity gates. Okay, so in the table, this is showing again what we had in the beginning. Post-selection BQE has an improvement of these metrics are just the average improvement in the energy and the max improvement. So post-selection BQE is a factor 2 better. Echo verification is factor 8 to 100 approximately. And same with post-selected virtual distillation. Oops. Okay. The nice thing about this is as we can scan the system size, we can look at the mean absolute error as we increase. And so the nice thing is that we see that actually with post-selected BQE, with post-selected virtual distillation and echo verification, we actually have sublinear scaling in the error as system size goes up, which is pretty great. The bottom boxes down here are actually a superconducting order parameter. Since this is a pair correlation model, this is mostly to show that we're getting this discontinuity correct with respect to PCS and PCCD. So the experiment is sort of performing as expected. I'm going to wrap up with just this chemistry data, since that was the original context of this. So we really wanted to go beyond the 12-qubit system, but even with these powerful purification techniques, it was quite challenging for 10 qubits to be commensurate with the system we were looking at. So the system we have here is actually a cyclobutene ring opening. So that's 4 carbons with some hydrogens on it. What we do is we rotate the bond such that it goes into butadiene. So this has a nice reaction barrier. In fact, most of this is actually single reference. That's what got the Nobel Prize over Hopper rules. So what we're looking at here is an energy metric associated with cathode dynamic correlation. Pretty much, can you use this type of technique in chemistry for chemistry simulations on these devices? The answer is largely no. The green curves here the green points here are the echo verification data on 6 qubits. 10 qubits is something that doesn't look exactly like this curve, or I think most chemists would say it's not correct. And then the 10 qubit data is sort of off this scale. And so even with these powerful error mitigation techniques, it's quite difficult to reach the errors that we want. And so In conclusion, I won't put up the full author list here. Doing one of these experiments involves quite a lot. Summarizing it very quickly is difficult. It involves a lot of effort from the whole group, really. That's why these get quite long. But variational algorithms are quite challenging, and I think the Harshad example still holds the record. But these generalized purifications are quite powerful. They might be useful in a lot of other scenarios. And we've seen sort of a slow shift towards dynamics problems, which would definitely be an interesting area to go towards. Thanks.
Okay, thanks a lot for the great talk. Do we have any questions? Right, I was wondering, so you showed some scaling the system size of the error. Is there some intuition for this in terms of the model that you're simulating?
Not particularly, because it's using the same circuit as the chemistry Hamiltonian, which we see a slightly worse scaling error, which I didn't show. I think the fact that it's just sublinear is sort of encouraging, but I wouldn't derive too much from this overall scaling.
Okay. So do you have some intuition for kind of chemistry Hamiltonians in general, how these sort of methods should scale?
In terms of the error with respect to unitary pair-coupled cluster doubles or something else?
Yeah, maybe in general, I don't know.
Yeah, so these seniority zero Hamiltonians, PCCD works extremely well in general. Formally, they're still difficult to solve, but like something like DOCI, QMC has traditionally performed quite well. So in electronic structure, they're actually viewed as sort of like a cheaper addition that you can add to a multi-reference calculation to try to recover dynamic correlation.
Cool. Okay. I see no further questions. So before we thank Nick again, I just wanted to mention, please stick around because there are going to be 2 announcements. But let's thank Nick.